All right, after graphing quadratic functions, now we're going to analyze a little bit more about these graphs. We're not just going to draw them, we're going to identify some special features about the graphs. Okay, so step one is just to go ahead and graph the equation. Notice that this one is in standard form, so the only way to graph it is to first find your vertex. Remember, to find the vertex from standard form, you have to do negative b over 2a. Okay, so a is going to be 1, b is 4, c is 3. Okay, so negative 4 divided by 2 times 1 is going to be negative 2. Remember, that's the x value of your vertex. How do you find the y? You plug it in. So negative 2 squared plus 4 times negative 2 plus 3. That's going to be 4. That's going to be a minus 8 plus 3. Negative 4 plus 3 is a negative 1. So the point negative 2, negative 1 is your vertex. From there, I can go ahead and draw the rest of my graph because I know it's going to be 1, 1, and then 2, 4, 2, 3, 4. And if I wanted to keep going, and I'm going to, just for fun, it would be 3, 9. And here's my graph. Okay. I could go ahead and fill in some points here using, maybe I would start at my vertex, and this would be like negative 3, negative 4, this would be negative 1 and 0. I'm just going to go ahead and fill these in. So I know that this was at 0, 0, and this was at 3. Okay. Your axis of symmetry. Can you draw a line that would cut this graph perfectly in half? Okay. It would be a vertical line that cuts right through the middle of that. That is your axis of symmetry. Axis of symmetry is the equation of the line that draws that cuts the graph in half. That's just going to be x equals the x value of your vertex every time. X equals the x value of your vertex. Would you say that this graph has a maximum or a minimum value? Okay. It's going to have a minimum value, and that's going to be this lowest point on the graph. That's here at negative 1. Okay. Domain. What is the domain of all quadratic functions, if you remember from transformations? It's always going to be all real numbers. Range. Here, y is going to be greater than or equal to negative 1. If you like using inequality notation, remember you could use interval if you would like. That's going to be negative 1 to infinity. Always parenthesis on the infinity. That's up to you. Roots. Remember, the roots are your solutions or your x-intercepts here on this graph. Looking at this graph, your x-intercepts are going to be either seen here, where y equals 0, or you can just see them visually here on the graph. So the two roots, and you should have 2. You could have 1. You could have none, but never more than 2. Those are your two roots, and I've now analyzed this graph. Okay? So we started off with kind of the hardest example, looking at question number 2. This equation is in vertex form, so remember I already know what the vertex of this graph is. This tells me it moves right 2, doesn't go up or down, so 2, 0 is going to be your vertex. So that's right here, 2, 0. From there, I know the 3 in front tells me that this graph has been stretched, so over 1 and up, 1, 2, 3, 1, 2, 3. Usually it would be 2, 4. Now it's 2, 12, which is way off this graph. So those are the only 2 points I can really draw. I could go ahead and fill out the table, though. This is going to be 2. This is going to be 1, 0. This is going to be 3, 4. 2 is at 0. 1 and 3 were both at 3. Remember, the next point would be 2, 4, but now it's 2, 12. So these would both be at 12 if you wanted to know. After that, what is the equation of the axis of symmetry? Remember, that's this vertical line that's going to cut the graph in half. The equation of the axis of symmetry is always x equals the x value of your vertex. Does this graph have a maximum or a minimum? It's going to be a minimum again, because it has that lowest point, and the lowest point is there at 0. Okay? What about the domain of this graph? Again, we have a quadratic, so what is your domain? All real numbers. What is your range? y is greater than or equal to 0, or if you prefer, 0 to infinity. And then roots. Okay, so like I said, the first one had 2. This graph only has 1. Since the vertex is your root, then that is going to be the only one you have. Technically, that's called a double root, whenever the root is your vertex. Okay. Last example here. Okay. This one's in root form, so remember the very first thing, I already know that my roots here are going to be 2, 0, and negative 2, 0, okay, because remember you just change the sign on both of these, or find your solution there. So here's 2, 0, and negative 2, 0. Remember the vertex is always going to be halfway in between those. So halfway in between is going to be 0. Remember to find the y value of your vertex, you plug 0 in for your x's. So that's going to be negative 2 times 0 minus 2 times 0 plus 2, or negative 2 times negative 2 times 2. Negative 2 times negative 2 is going to be positive 4 times 2 is 8. So 8 is the y value of your vertex. So 0, 8. From there, I know this graph has been stretched and reflected, so usually it's 1, 1. Now it's going to be 1, 2. Then it would be 2, 4, but now it's 2, 8, which is good news because that's where I already have my dots drawn for my roots. It's not my best graph. Okay. I can go ahead and fill out some points. 0, 8, 1 is going to be at 6, and 2 was at 0. Okay, we knew that because those were our roots. Again, your axis of symmetry, the vertical line that cuts this graph in half, that's going to be at x equals the x value of my vertex, or 0. Does this graph have a maximum or a minimum value? Since it has been reflected, it's going to have a maximum value at the y value of your vertex, which is 8. Domain, again, all real numbers. Range, y is less than or equal to your maximum value, or if you prefer, negative infinity to 8. Remember, you have to flip around your interval because you have to go from least to biggest.